Hello, welcome to today's video where we're going to be looking at how to do volumes of revolution but between two curves. Dun dun dun. However, if you're watching this video, I'm assuming you already have a general understanding of volumes of revolution, and if that's not the case, I'd recommend pausing this video and instead going back to one of my other two, or even both of my other two videos explaining how to do volumes of revolution at a base level. But a quick recap, if you have a region between a curve and the x-axis and you want to generate a volume by rotating that region 306 degrees about the x-axis, all you got to do is use the formula pi lots of the integral of y squared with respect to x. Whereas if you have a region that lies between a curve and the y-axis and you want to generate a volume by rotating that region about the y-axis, then you use the different formula of pi lots of the integral of x squared integrated with respect to y. However, in both of those scenarios, the region we were rotating to generate the volume always was in between the curve and one of the two axes. What happens though instead if we want to use a region that lies between two curves? Well, good news. All we've got to do is to use a very similar idea to what you use when you're trying to find the area in between two curves. For this particular first example or first explanation, I'm going to look at doing volumes of revolution about the x-axis, but between two curves. Okay, as you can already see, I've also labelled my two curves. So the curve that's at the top, I've labelled as y equals a function of x, that's called f of x. And then the curve at the bottom, it's going to be labelled as y equals g of x, a different function of x. So what you could start off by doing is you could do volumes of revolution with the curve at the top, and that would do volumes of revolution with the region in between that curve and the x-axis. That would be found by doing pi lots of the integral of f of x all squared integrated with respect to x, because of course it's normally pi lots of the integral of y squared with respect to x, and as y was equal to f of x, I replaced the y with f of x. It's also worth pointing out we should have our limits. Now, admittedly, from the way my diagram looks, it looks like the bottom limit should be 0, which would be the case, but let's be more general and just say it's starting horizontally at x equals a and finishing at x equals b, then therefore my limits would be a and b. I could then also try and find the volumes of revolution generated by the curve that's at the bottom, g of x, and that would be using the region between that curve and the x-axis and doing volumes of revolution with that. And that would be pi lots of the integral from a to b of g of x all squared, and we'd be integrating x's for that. But you might notice in both of those cases we have not found the volume we want. The volume of the first curve was finding too much volume because it was starting below f of x but then going all the way down to the x-axis, which we didn't want. And then when we were using the curve at the bottom to do volumes of revolution, that was finding a region we didn't want at all. But the good news is, just like integrating to find areas between two curves, the way these two things link up is exactly how we want them to, because all of the extra area included by doing volumes of revolution with that first curve is entirely also covered by the volumes of revolution caused by that second curve. So all we've got to do is the volumes of revolution caused by the curve at the top, subtract from that the volumes of revolution caused by the curve on the bottom, because that will then just take away all the extra volume that I don't want. Nice! That's all there is to it. So if we're then doing an example, let's take a look at an example like the one we've got on the screen right now. We've got two curves. We want to find the volume generated by rotating the region between those two curves 2 pi radians about the x-axis. We've got the equations of the two curves, and also our region is starting at x equals 3 and finishing at x equals 4. So the way we'd do that is we'd first start off by doing volumes of revolution with the curve that's at the top, which is the y equals 1/3 x squared. So therefore that would be pi lots of the integral from 3 to 4 of 1/3 x squared, but then because we're doing volumes of revolution, we've got to square that, and then we're going to integrate that with respect to x. And then we're just got to later on take away the integral, well, actually pi lots of the integral, from 3 to 4 of the square root of x cubed minus 6x squared plus 12x minus 8. Again, all squared because it's volumes of revolution. And again, we're going to be integrating that with respect to x. And if we work out that will find the volume that we want. And so progressing on with this, the first thing we'd do is deal with the fact we're squaring both of those functions before integrating. So therefore this first integral would actually be the integral from 3 to 4 of the 1/3 squared, which is 1/9, and the x squared, which is x power 4. And then also we've got the integral from 3 to 4, the pi in front of it, of course. And luckily the square root and the squared are cancelling out. So this is actually a very nice one, despite at first looking like it would be a horrible one because of that square root. Then we just got to do the integration itself. So therefore that would be pi lots of, and then we're going to use the square brackets now because we actually are doing the integration. So therefore that's x to the power of 5, and then there'll be a 1/45 out the front, the classic add 1 to the power, divide by the new power sort of skill. And then the limit's 4/3 written like that. And then we're going to take away pi lots of the other thing integrated, which of course would be 1/4 x to the power of 4. We'd have a minus 2x cubed. We'd have a plus 6x squared. And we'd have a minus 8x in all of those cases. Adding 1 to the power, dividing by the new power because we were just integrating polynomial expressions. So therefore we also got to have the limits 4 and 3 there. From this moment on, it is ultimately number crunching. I would once again recommend being really careful to make sure you're carrying forward that pi throughout the entire question. Although it's tedious writing it out, then that does take up more time. The biggest mistake a lot of students do is they go, oh, it's alright, I'll remember to deal with the pi at the end, but then having done all the effort of doing the integral and everything, it's very easy to then just forget that last step of multiplying by pi. Whereas if you write it every single time, you're then not going to forget it because you can still see it there. So therefore now dealing with the limits, we're going to have pi lots of course, 4 to the power of 5/45. Take away 3 to the power of 5/45. We're then going to have taking away pi lots of 4 and 3 plugged into all this, which is then a bit tedious to write out, but it's a good idea to do because of the way method marks work. They often give you a method mark for showing you understand how to plug limits in. So then if you make a mistake with the number crunching when you come to plug into the calculator, you've at least shown, look, I know what I'm doing. So this is me just writing all of that out. And I'm running out of room, but we just about managed to cram it in there. We need an extra pair of brackets technically. There you go. Cool. And then for the sake of completeness, where this ends up heading is I'd work out this first little bit of an integral, and that comes to 781/45, lots of pi. And then the second integral with the limits plugged in will come to 15/4, lots of pi. So then combining those two things together, that will get a final answer of 2,449/180, lots of pi if we're writing it in exact form. There you go, that is the answer to that example. But then dealing with a few other little details I want to mention. First of all, what happens if we're doing volumes of revolution between two curves but rotated about the y-axis? Well, you might have noticed before when I was talking about doing volumes of revolution between two curves about the x-axis, I was using this idea of the volumes of revolution with the curve on the top minus the volumes of revolution caused by the curve on the bottom. However, that was talking about, where they were in relation to each other vertically, because I was doing volumes of revolution about the x-axis, so therefore the vertical height is what matters there. Whereas because we're now doing volumes of revolution about the y-axis, therefore what's going on horizontally is what matters more. So if you're doing volumes of revolution about the y-axis, for this scenario, instead I'd do pi lots of the integral of f of y, in other words the curve that's further to the right first, or in other words further away from the y-axis would be a better way of wording that actually, minus the integral of the curve that's nearer to the y-axis, which would be g of y, and again squaring it because it's volumes of revolution. And so that's how you do volumes of revolution between two curves about the y-axis. And the other thing I'd like to remind you about is that it's important with this stuff that you do the squaring of the functions before you start trying to take away anything to do with them from each other. So that meant, for my example, I did them as two entirely separate integrals, partly to help me remember that I have to do the squaring and the integrating before I then end up doing the taking away. However, you could choose to do the volumes of revolution between the two curves all as one big integral if you wish, but most of the time you're at no benefit to do so. However, there is an odd situation where that might be beneficial to do it all as one big integral. Let's say we had one curve that was like something like y equals 3x squared, and then a separate curve that was something like y equals x squared, and we're doing the region in between those two curves. Well, in that case, it would be a benefit to do it as one big integral, as long as you remember to square the functions before you do the subtracting. Because if we do that, then it will actually save some time on how much integration we have to do, and also how much plugging in numbers into the functions that we have to do after the integrating has happened. Because we'll do 3x squared all squared, and then take away x squared all squared, and of course we're still integrating with respect to x. And of course there'll be the pi out the front of the whole thing, and of course we'll have the same limits for our two things, so a and b, whatever those are. The reason this though has helped in this particular scenario, doing it as one big integral, is that because both of them involve x squareds, some of the terms are going to nicely, or in fact in this case all of the terms are going to nicely combine, which then means I've got less to deal with. So for instance, 3x squared all squared is 9x to the power 4, and x squared squared is x to the power 4. So therefore that means you can then simplify the integral before you're actually having to try and do the integrating itself, which then means you would have less to deal with in the long run. As I said, that made sense for this scenario because these were terms that were going to simplify or combine, whereas if that's not the case, it really doesn't matter whether you choose to do the integration then the subtraction, or the subtraction then the integration. But either way, the squaring is what has to happen first. Okay, hopefully you found today's video useful. I shall see you in a future video. Goodbye.